Who wants to do this? Who knows what double expected search is? Oh, no, double Q learning. Double Q learning. That's in the book, right? Does anyone know double Q learning? What is double Q learning trying to do? Getting rid of maximization bias. Oh, okay. So in Q learning, we have maximization bias. How come? Where is it coming from? What is bias? What is bias? Does anyone know what bias is? What do we mean by bias? Yeah? You were nodding, you know? Do you want to say? Give me your version.
Like, I don't know how to put it in a word.
Just try.
How much?
Yeah. Maybe a simple scenario would help, right? Like in a simple case, what's bias?
Like if you have like a model,
Okay.
it could have some initial bias or.
Oh, we are using bias for many different things, right? And so one of the meanings is that we are kind of, it's a preference, or almost like feels like in that meaning, right?
Yeah,
it's like, yeah. Although it might not be an explicit preference, but it's kind of shifting away from maybe what's spot on, right? To for whatever reason. That's kind of the general meaning of bias. Yeah. So in statistics, people use bias with some really specific meaning. So let's say, very simple scenario, you're trying to estimate an unknown mean given some data from some distribution whose mean you want to know. So you have this data, maybe it's IID, it's a sequence of these observations, and you construct an estimate of the mean with some way. So just a function of the data, like you process the data, you spit out a number. What's bias? When is this biased? Estimator of the mean.
Isn't it how much the expectation deviates from the mean?
Right. So you produce an estimate of the mean, and then you look at on expectation, how much does this deviate from the mean? Maybe I write this down. Of course not. Where is the eraser? It's hiding here. Okay. Okay. So the situation is as follows. You have n observations from some distribution over the reals. You're interested in estimating the mean of this distribution. So you take the first data, you take its expectation, that gives you the mean. All of them are from the same distribution that have a common mean. You want to estimate this. So let's assume that, well, they're identically distributed according to P. They're independent to make the situation a little bit easier. An estimator is going to be a function that's given this n data point. It returns you some value. It's just a function. So if you'll apply this to your data, since the data was random, this is random. We can take its mean. And if this is not 0, if this difference to the mean, difference of the expected value of the estimator, is return on the data, and the true mean is non-zero, then we have a biased estimator. And so we call this the bias of F. On this, okay, it also depends on the distribution P, but like, so this is a bias of this estimator on this distribution. Yes. You don't need to know the true mean to talk about whether something is biased or not. Waha.
How do you know if it's 0? How do you know
Yeah, that's where proofs come into play. You prove it's 0. So let's try something. So for example, we can take as the estimate of the mean just the sample average. This is your function. Okay, so it's like maybe this is lowercase so that you clearly see that this is just a function of these values. So fx1 to xn, let's define this as just taking the average of the inputs of this function. Now, if you plug this, like plug the data in, so we have this expression here. So what is that? So for this particular f, call it f mean, or average, or maybe average is better. Give it a name so that we know that we're talking about this specific thing. Well, just plug in the definition and use the linearity of expectation, knowing that these expectations are assumed to exist. You can do this. So each and every value here is mu. We have n of them. So we get n times mu divided by n. That is just mu. So if I subtract mu from this expectation, without knowing anything, we are sure that there is no bias. It applies universally. That's the beauty of proofs, right? No matter what the distribution P was, no bias. So there's a sample mean. The sample mean is not necessarily the best estimator. If you have distributions which are spreading out a lot, people call it heavy tail or something. It's like with low probability, you observe really large values. Then somehow the sample mean is not too robust. It's like the sample mean is not going to give you a value that's close to the true mean, even if you have a lot of data. You can improve upon it by kind of doing something with this extremely low probability but very high values. Trim them away, do a bunch of other things so people can improve on the sample mean in scenarios like that. And these are important, for example, when you're talking about floods or natural disasters of that form, then you do have these distributions. And if you were using the sample mean, it would be not a good idea, because the sample mean is not going to be very close to the mean in some probabilistic sense. You can improve upon it. If you do this, like for example, you decide that I throw away every value in my data that's further away from, I know that my, I don't know, my data is non-negative values because it's about floods, like water levels in rivers or something like that. Then you say that, oh, I throw everything away that exceeds a certain number because those are so extremely impossible, and they're just going to cause me trouble with controlling how much my estimator deviates from the true mean. You do that, you take the sample average for the rest of the data, so it's called trimming. It's not going to be unbiased. You buy a little bias, introduce a little bias, but since we said that, oh, those observations have a very low probability of happening, the bias that you're introducing is relatively small, and the benefit of that is that these values would be pulling very far the sample mean from the true mean. So you got rid of them. You're not taking them into the average. So now your average is going to tend to be much closer to the true mean. You're kind of reducing variance. So this kind of a bias variance trade-off that people are talking about a lot. This is the simplest scenario when it applies. That's the reason we introduced biased estimators. Being unbiased is not necessarily that helpful. You want to be concentrated around the mean. So it's not like that bias is just bad. No, sometimes you want to introduce bias to help yourself. But anyway, so this is bias in a statistical sense, and it doesn't have any directionality and intended meaning of being bad or good. It is just a definition. It's like deviating from the mean. You want to estimate some quantity, your estimator on expectation deviates from it, then you say it's biased. So this is the sense in which sense we're talking about the bias in Q-learning. That in Q-learning, we have an upward bias for estimating the mean. Or estimating the actual value. In that case, it's like there is a true Q values that you're trying to estimate. And then if you plot the distribution of the estimated values across a lots of simulations, you could plot distributions, right? So you run simulation for, I don't know, 100 steps. And at that point, you stop, and then you plot the distribution of the Q values. And then it's going to be like Q values at a particular state. I don't know, you have state number 100 and action number 3, and you plot the distribution of it. You get some distribution like this. And if you calculate the mean of this distribution, it's kind of, I don't know, like it has some heavier tail, so maybe the mean is here of this Embriger distribution. And the true value that you're trying to estimate is going to be here. So this is, I don't know, it's Q-learning, so it's Q star, lowercase q star, 103. And so if you would run these experiments, you can plot this, you can look at it, and you will see this upper tail. So this is called the upper tail of the distribution, lower tail of the distribution. And this is just a histogram here. Okay. So why does this happen? That's the first question. So in Q-learning, we have this thing that in the update, we are taking the maximum of random quantities. And if you're taking the maximum of random quantities, and maybe the random quantities itself are unbiased, that would be the lucky situation. Maybe they already have some bias. But let's say they're unbiased. So kind of this is the situation. So you have, I don't know, fixed state, or maybe there's only one state. It's kind of like you are in a bandit. And then you're estimating the rewards for all the actions. You have these estimates of the mean reward for all the actions. So for action, how do we call the actions? I want to call them by 1 to k. So there are k actions. These are going to be random. So these are estimates of mean rewards for actions 1 to k. So you put each of the actions, like an action, you put a certain number of times, you take the observations, you took the sample mean. These are themselves unbiased. Okay? We're in the bandit. We're going to come back to Q-learning, but you will see that bandits is like a nice playground where it's easy to understand what's going on. Okay. So if you want to estimate not this, but the maximum reward that you can get. So sometimes we just call this mu star. So the question is this. How do you do this? You have this data. You save the data. You calculated maybe the sample means for all the data. So one simple way is just taking the maximum of x1 to xk. The question is, what's going to happen? Hmm?
You always take the highest. You always pick the highest and don't make it more anymore unless the highest value accomplished.
Well, we kind of stopped exploring here. We're done with exploration. We pulled each arm a certain number of times. We just collected data. So now someone just asked you, in this bandit problem, what's the maximum reward that you can expect to achieve? And you have to answer, okay, the maximum reward is this and that. So one simple way is just to take the estimated means of the rewards for all the actions and take the maximum of them. It's kind of very simple approach. Okay. The problem is that if you do this, even if these are unbiased, so they have the correct means, they are random. So if you have so let's say most beautiful case when everything should work beautifully. Let's say extreme case, all these values are the same. They are mu star. All the arms are equally good. Okay. If I told you this, would you use the maximum to estimate mu star, which is the common mean across all these samples? Probably not. Maybe it's better to take the average of these. Let's say we put each arm equal number of times, and the variances of the rewards are the same for each of the arms. This is a very simple scenario. You would just take the average, right? that would be unbiased, and that would be kind of like spot on estimator. If you take the max, what's going to happen in this case? It's like you have this k random draws from a distribution with a common mean, and you take the maximum of them. Do you expect that this maximum is going to be above or below the true mean? Yeah. Has to be above. Was this? That's an interesting. So, okay, I don't know what you mean by keep doing it. Can you explain on that, or explain that?
If you were in this state, like in this matter problem multiple times, you keep picking the max. The max, like, should like by law of, I don't know, but it should converge to the right?
Yeah, we wish that somehow we converge. So let's get to that very quickly. So what happens, we can again draw a new graph for this, is that, so very simple. Yeah, something to do with the variance. So here's our mu1, which is the same as mu of k, which is the same as mu star. And that's a very simple scenario. These are normally distributed. So all these random variables are from this normal distribution, whose mean is this common mean, and they have the same variance. Simple setting. If you draw k of them, well, they're not going to be exactly spot on. They're going to be, I don't know, at some places, right? The more you draw, the more likely you're going to find someone in the tail far away from the mean, left or right. With the max, what we are doing is that we are looking at the leftmost guy. It's like the larger the k is, the further away it's going to get from the mean. Okay? And it depends on the variance. So if you make the variance larger, then again, it's like you're just spreading out this graph. And so we expect that the maximum of these random variables, mu hat, is going to be biased in a positive fashion. So you expect that the expectation of mu hat is going to be larger. And the larger k is, the bigger this difference is. Or like, let me put it this way. If you subtract mu star from it, it's going to be non-negative, and eventually it gets positive, or like, actually for even k equals 2, it's already going to be positive. And as k gets large, it gets large. If the common variance gets large, this gets large. So you will have a large positive bias, upwards bias. Okay.
But at the end of the day, it's still the best action, so it doesn't really matter.
Well, if someone is asking you, like they're not asking you to tell me what the best action would be, but they are asking you, give me your judgment of how much reward I'm going to make if I keep choosing this action in the future. And then it turns out that just choosing the best action and looking at its statistics is going to give you a biased, upward biased, optimistic estimate of how much they're going to make. So if the person is worried about this optimistic, the estimate being optimistic, then you better use something else. And one of the simple ideas could be to split your data. Half of the data goes into estimating the means. The other half of the data goes into estimating a second set of means. Use the first half to estimate use the first half to figure out what action to choose. Use the second half to figure out what the mean of that action is going to be. Since the two samples are independent of each other, this procedure has no bias. You solve the bias problem. So this is the idea underlying double Q learning. So in double Q learning, you're worried about this optimistic bias. Maybe it's going to harm performance, and you want to fight it. And the connection to this bandit setting is that in Q learning as well, you're estimating, okay, not the maximum. Like you need to update the maximum of the action values over some actions. So that's very similar to this bandit situation of like, give me an estimate of how much reward I could make if I choose the best arm in the future. That's kind of the same question, but asking for these action value functions. And double Q learning does this splitting of the samples in a certain way, and it tries to fight a bias this way. All right, so we're kind of running out of time. I have a bunch more to say about this, so maybe we just continue on Friday with double Q learning and all of these things. There are some very interesting things that are happening here. Right, thank you.